asking a really sensible and good question, to which the answer is I don't know yet. But I'm about to find out now that you asked.
Right now, this second.
Literally, I'm hitting the syllabus and finding out, because I don't memorize them. I have 5 classes. Oh, your final
find out
is
the finals today.
No, your final is on Thursday, the 17th, 10 till 1. Okay? So Thursday, the 17th, 10 a.m. to 1 p.m.
Got a little over a week then.
Yeah, a little bit. But we're pretty done now. I think I should get started. So good morning, everyone. Really tying up loose ends today. We're going to look at just another basic last example, actually, of a hypothesis test on the difference between two means. And this is a version of question 8. I'll give you a little background to the story, but this is pretty much the main part of it. They were conducting a test to see if the number of hours sleep was different. The average number of hours in which someone slept for liberal arts students was somehow different from non-liberal arts students. Well, we all know that liberal art people are lazy and they sleep a lot. So the evidence that they've got here is that population 1, which are the liberal arts students, on average sleep for 7.67 hours. That's the average number of hours they slept for. And non-liberal arts students only slept for 6.82 hours. So there's definitely a difference. In this story, they want us to find conduct a hypothesis test to see if we can prove that there is a difference between them. So we're not trying to prove that one's bigger or less, we're just trying to prove that they're different, right? Because that's one of the 3 hypothesis tests. So mu1 is liberal arts people, mu2 is the non-liberal arts people. Here is the data, 25 of them, that's the data we got, 148. Here is the data that we have. And we're being asked in the question to do a 5% significance level. Kind of middle of the road. And this number here we have to treat as magic. Technically speaking, if you never told me that this is the degrees of freedom that I should use, wouldn't I be using 24, which is the smaller of the 2? Now, if you're wondering where this thing comes from, if you go look in the textbook, there's a really big, massively ugly formula where you plug in numbers and it pops out with 38, essentially. A good rule of thumb is obviously the smaller sample, take away 1. In practice, the difference between the 2 is negligible. You very rarely ever get a different conclusion. But they said 38, so just so that we get the right numbers when we do web assign, we'll use it. If they didn't say 38, you would have chosen 24, right? That would have been your choice. And so we have the null hypothesis, which when you do 2 means, a difference between 2 means is always this, and a not equal to 1, right? And a not equal to 1 is a two-tailed, isn't it? Okay, so we're going to go through the kind of the calculation process. So I would like to know that guy. So 7.67, take away 6.82. 7.67, take away 6.82, and the answer is nothing 0.85. I'd like to get the standard error. We are assuming that we're not going to pull this data because none of the questions that I will give you will be. So that's the formula for the standard error. So it's going to be 1.34 squared divided by 25 in that sample. And in the other sample, it's going to be 1.74 squared divided by 148. Hang in here, we have got 1.34 squared divided by 25, add 1.74 74 squared divided by 148, and the answer is 0.30. What kind of accuracy are they asking for? What are they asking for? Brilliant. They don't tell me what they're asking for. So I'll make a executive decision and we'll do 3 decimal places. So we're now going to move to the next phase, which is we calculate what is called the t-score. I think it was someone in the class went and asked in a homework question, what do they mean when in some of the questions they ask for the test statistic? I think they use that phrase. That's the guy. So either the z-score or the t-score is what they're calling the test statistic. As far as I could tell, that's what it was. Now, for a t-score, it's the data, right? So it's those two guys divided by the standard error. So it's a 0.85 divided by a 0.304. And I get a 2.5. It's a pretty nice t-score. If it was a z-score, it'd be a really good z-score, right? But for a t-score, they tend to be bigger. So that might not make it. So after you find your statistic, your t-score, you find the p-value. Now, it's a probability, but because it's a not equal to, right? It's a not equal to story. It's the messy one. It's the one where it's between the two values, right? And I'm going to do salt now, because that's essentially the only way we can get this information. And hopefully you are looking at the salt one, right? Now, I don't know why this one is on one sample T, which it should be, but normally when I do these, oh, there we go. It's on normal distribution, right? And I go to T distribution, right? And I go to both tails. And now I can type in the 2.5 that we had. And I do it on both sides. And our p-value pops out at about 0.031.
We've got to put in the degrees of freedom.
In space I did, well caught. And the degrees of freedom are 38. That will change virtually nothing, but it could have made a big difference.
But then you have to re-enter the negative. Yeah.
Oh, that's not good. Because when I changed the degrees of freedom, the other guys changed. It did make a difference. Quite a substantial difference. 0.017. Okay, I can look with that. And after not being careful about degrees of freedom and tweaking it, we finally got the right number. So we're on to the test then, which is our p-value less than our significance? Well, is 1.7% less than 5? And the answer is yes, it is. So we can say our conclusion we have enough evidence to reject H0. You see what the choices that they have. So we have enough evidence to reject H0, and so we can conclude that HA is true. And in English then, there is enough evidence to prove that there is a statistical difference between the two groups. But we've managed to prove that liberal arts students do sleep a different amount than non-liberal arts. And that's the last question that we are going to be doing that's new. So let's tidy up some things. Things to look out for in any hypothesis test. First one is the data unbiased. Okay, I think they have a phrase in computing, it's called something like garbage in, garbage out. You heard that phrase? Garbage in, garbage out. Basically, if you start off with bad data, you can do the best statistical analysis in the world, but the answer is useless. Now, we know tons of different ways of getting biased. And can't we get biased by asking the question in a bad way? We can get biased by not asking a random sample, right? We can get biased by not asking enough people. Oh God, the list is endless. Isn't it easier to make it, to screw it up than it is to get it right? There are lots of ways of screwing up and only a few ways of getting it right. So you want to make sure that when you collect your data that it is unbiased. The major things that you can test are the size of your sample. Now let's remind you what that is. If you are doing questions involving proportions, right, what percentage like Pepsi? The test for size is that NP has to be bigger than 10 and NQ has to be bigger than 10. You remember that? Sometimes we bother to check it, a lot of the time we just assumed it was true. Agreed? Now, if it's two different samples, don't both the NP1, NQ1, NP2, NQ2, doesn't everybody have to be bigger than 10? Now, when it is means, big is a little bit more problematic. A kind of rule of thumb is that it should be big in the sense 30 or more is a decent size sample. You know, 300 is better, right? But at least 30 is a good rule of thumb for sample sizes. So that's size. Now, shape of distribution. If it's proportions, you don't need to check. If you do a question and you ask someone and it's a proportion question, the mathematics tells us that it's going to be bell-shaped. You don't need to check it, they always are. As long as the sample's big enough. If you did the sampling distribution, it would be fine. When you are doing questions involving means, you should do a sketch of the data. We have not done that, mostly because every question that we got, it was assumed that the data was roughly symmetric. It only needs to be actually roughly bell-shaped, if you want to be really specific. So as long as the data that you're getting your information from is roughly that shape, everything is okay. Now, what could screw things up? An outlier will kill you stone dead. Can you imagine I collected some data on the wealth of people and I got a random sample of 100 people and I asked them the question and I got the truth. But you know, it was one of those days, we all have them. And guess who I asked? One of the people I asked was Bill Gates. Hasn't my data basically got annihilated with Bill Gates? Won't the mean of the 100 people be everybody's a billionaire? Virtually. Now, the data is corrupted, right? It's totally spoiled, right? Now, if I ask people, are you in favor of abortion? And one of them was Bill Gates, wouldn't have no effect. Isn't his opinion on abortion just as good or bad as anyone else's opinion? So do you see how proportions don't really have to deal with outliers? Because there's only two answers, yes or no, right? There isn't really an outlier option. But when you do data, right, you collect numbers from people, couldn't you get a really bad big number? So when you look at your data, sketch it. If you see an outlier, what should you do? Because you still want to do a hypothesis test. I got Bill Gates and my 100 people. What should I do?
Toss them out.
Toss them out and just have a 99 sample. And as long as when you do your report, you say, one of our data points was Bill Gates, I deliberately removed him from the data set because it's clear to me and probably the rest of the universe, he is an outlier. And as long as you can convince people that the reason and only reason you threw that one data point out was it was an outlier, then most scientists will look at you and say, yeah, you know, everybody gets an outlier from time to time, you know, that's fine. Second is skewed data. It's okay for the data to be roughly symmetric, which means it can be a little bit big on one side, a little bit small on the other, and that's fine. You do not want data that is skewed. If the data is skewed either to the left or to the right, you can't do a hypothesis test on it. And it's to do with the fact that the sampling distribution just won't be bell-shaped enough for you to get good numbers. I mean, you'll get numbers, but you can't really believe them, right? The theory says, the t-distribution theory says, that the data has to be roughly symmetric or else it's not really valid. So sometimes you have to find other ways to analyze the question, right? You just have to figure another way around the problem. You can't do outliers. You can't say, well, I'm going to cut off all these people because if I cut them off, it looks roughly symmetric now and I'll just use, you know, the 70 that's left and I had to throw out 30. Because when you start doing that, aren't you really doing quite serious surgery to the data? You're distorting it in some way that it becomes meaningless. So you just accept that sometimes you can't do it, and that's fine. Lastly, other shapes. Imagine when you looked at the data, right? You collect your sample and you make histograms of it, and darn it, it came out looking like that guy, a double hump. Right? That's going to kill your data. Your analysis won't be good. And just like skewed, you can't fix it, right? There's no fixing this one. It's just dead. And that's sad, but it is what it is. Do you know that is not that uncommon? Do you know if I collected data on the heights of adults, it would look like that? Why would, let's say I collected 1,000 people's heights, right? Males and females. And I made a histogram of it. How on earth would I end up with a data shape like that? You might have thought that the answer was, oh, you just get one of them. Why do you get a double bump? Any ideas?
Because of the two sexes.
Yes. What you're really doing here is you're merging together two slightly off-centered normal distributions. And when you put them together, when you see a two bump, it almost always means that there's two distinct populations that you've stuck together and considered them like they were all the same. And I'm not being sexist, but males are typically taller than females. Would you all agree that's a reasonable generalization? Now, do you 6'6" women? Of course you do. Do you get 5'2" men? Of course you do. But on average, aren't males typically taller than females? And that's why you get a double bump. You get a double bump if you did their weights as well. Aren't males typically a little bit heavier than females for the same reason they're taller? Can we go? Let's suppose we fixed the data, right? We checked the shape. What's left? There are problems in your conclusions. Let's suppose you did a hypothesis test, right? And your conclusion was not enough evidence to reject H0. A lot of people think that means, and it doesn't. They think that means the H0 is true. It doesn't mean that. So imagine I did a hypothesis test. And the null hypothesis was that the percentage of Scottish people who have been to America was 70%, right? And the alternate was that it was less than 70%. And I did the hypothesis test and I came back with not enough evidence to reject H0. Let's say that the data I got was 68%, right? Just because I didn't find enough evidence to prove that this was true doesn't mean that this is now true. All that really means is that we don't know. It could be that the right number is exactly 70%, but couldn't it also mean that the right answer was 69.2%? Right, for Scotsmen. You can't make any conclusions whenever you get not enough evidence. Basically, that's the end. You spent a lot of money and a lot of time and you don't really know much, except there wasn't enough evidence to prove that this was true. That's all you've got. Sometimes you get a conclusion, right? You prove that HA is true. And let's suppose that we have medical procedure that is 95% successful, right? So you're doing a heart bypass operation, and the way you do it, 95% of the people leave the operating table and they're still alive, right? Or they're alive in 5 years, which is a more typical way of measuring success in many operations. Right, so it's a 95, and that's the null hypothesis. and there's this new super duper keyhole surgery thing, and you've proved that it's better than that one. Right? And you got the evidence and everything worked great. And so you would say, yeah, the new procedure is better than the other one. But let's suppose that I used a huge sample, right? Because there's lots of people doing the old way, lots of people doing the new, right? It's like there's two, you know, like there's certain operations out there that there are like maybe two main ways to do it. And some surgeons do it this way because they think that's better and others do it the other. So you get great data on it, 10,000, and you find out that this fella here, right, was bigger than 95. And I'm being silly here. It was 95.003%. In other words, it's better by that amount. So when you do a conclusion, there are two kinds of conclusions. There's statistical proof, right, which you get when you prove the alternate is true. And then there is a conclusion that says it's actually important, because some conclusions are unimportant. Would you agree that the difference between these two is so minor, it's really not worth worrying about? Right? On the other hand, if this difference was 95 against 99, wouldn't that be significant as an important difference? Not just a difference you can prove numerically, but a big enough difference to make it maybe worthwhile telling the surgeons, look, okay, that's very successful, but this is even better. Why don't you learn how to do this operation? Because you're going to save a few more people, right? So it's not uncommon, for instance, for articles to say, oh, we have now just proved that people who drink coffee are more likely to catch cancer than people who don't, right? And you start worrying and you're thinking, maybe I shouldn't be drinking this cup of coffee in my hand neck here, right? Or whatever. And then you read the small print and you find out that the difference between the two, right, the normal population who don't drink coffee and those that do, that the difference between them is so marginal, like it's like 2 people in a million more die, right? In that case, shouldn't that article probably never have been published? Because it hasn't, you don't know the details. You don't know how big is big, right? Was it, you know, a 10% bigger chance of catching cancer, in which case I'm going to seriously give up coffee, which I don't drink anyway, but, you know, I would. Or is it like 0.02% extra? Yeah, I could get killed in a car accident more likely than that. So I'm not really going to change my lifestyle. So look at conclusions, but always look for this guy compared to the original number. Is that number usefully big, or is it irrelevant? Because statistics doesn't put a value judgment on a proof. It just says it's better. We need a joke to finish, and then I've got some new stuff to show you. Are you ready for a joke? Has somebody got one for me first? Because that'll give me a chance to think of a joke. Okay, Ashton, do you have a joke?
Oh, I don't. I should bring one.
Too late.
Maybe I'll copy one off the internet for next week,
Right.
or not next week, tomorrow.
Nakia, you should grab your little daughter and ask her for a joke.
She just went outside to play.
She probably heard that, and she says, I'm not staying about here. Okay, let me try and think of who I've not insulted. Did I tell you the one about the Pope? Okay, here it goes. The Pope arrives in New York airport and he jumps into a taxi and he taps the guy, you know, he's got one of those hook things and he taps the guy in the head, and he says, plane was delayed. I'm 4 hours late. I've got a big speech at the United Nations. I've got to get there in 10 minutes. Get a move on. Get there as fast as you can. And the taxi driver says, look, it's rush hour. There's no way I can do it. I'll do my best, but 10 minutes ain't going to happen. So he takes off, and 2 minutes later, the Pope's tapping him on the shoulder and said, look, you're not going fast enough. I'm not going to make it. Get a move on. The taxi driver says, look, I can't do it. He says, tell you what, if you think you can do it faster than I can, why don't you drive it? So the Pope says, okay, I'll drive. So they both get out, and the Pope gets into the cab, the driving side, and the taxi driver guy, he gets out, and he's just enough time to get in before the Pope puts his foot down in the accelerator. Front wheels go up and back wheels down, and zoom, he's off. And he's going up one-way streets the wrong way, and he's driving on the pavement. He's going round corners and two wheels. He is zooming. Of course, he gets pulled over by the cops. And the cop goes down and he taps the window, and the Pope brings the window down and he looks in, and the cop's was white. And he stutters and he backs off, and he goes on his radio and says, Sergeant, we're in real trouble. The sergeant says, what's happened? He says, I've just stopped the most important person in the world. And his sergeant says, you haven't gone and stopped the president. He says, no, it's not the president. It's somebody more important than that. And he says, who is it? He says, I don't know. He says, what do you mean you don't know? He says, I don't know. He says, well, how do you know he's important then? He says, well, he must be. The Pope's his chauffeur. Oh, come on.
That was funny. I'm laughing. I'm laughing.
Julia.
That was funny.
Somebody in this class has got a sense of humor. All I got from
laughing
David was
internally.
a smile. And Ashton is smiling internally. Cheyenne, was that a good joke? Nakia, was that a good joke? Okay, you're being honest. Julia likes it. Okay, so one of our class got it. I don't know. You think by now you get used to my sense of humor. Anyway, that was just a little break. So let's show you what the new thing is as soon as I close enough windows. And darn it, in space, I'll find it in a second. We're almost here.
Remember the Alt-Tab thing?
Oh, yeah. No, it wasn't so much that I got a thing inside that I haven't opened up yet. So, but yes, I do remember that's a cool thing that you showed me. Where the heck? Ah, here it is. Right. Okay. And let's show you what it looks like now. Basic. That's not right. Okay, what are you looking at right now? Are you looking at final exam practice questions with solutions? Oh, good, because it didn't look like that when I was doing it. If you go, hopefully this will still work, you may have noticed a new guy in town. Final exam practice questions and solutions. So I'll click on that again, and it should load up. Hopefully you can still see it. Can you still see it? Right, I'll put it on the full screen mode, maybe make it a little bit bigger. And when I get you on a week on Thursday, you'll be doing a final, not unlike this one, but there are a few differences. The first thing is that I've figured out my best way to do this, and the way I've finally decided is your entire final is going to be on a PDF. And then I'm going to set up in WebAssign a blank ignore me question that's got the salt button on it. So that when you need to go and use salt, you just click on that and you put your numbers in, right? So in WebAssign, there's just going to be a single blank, I don't care what the question is, it'll just have some with salt in it so that you can use salt, to find the p-values and any of the other bits and pieces that you need to to do. And I think that's less hassle than jumping between some questions on Web of Science, some questions on Canvas, and then you miss a question because when you flipped over, you didn't realize you hadn't done it. So that's kind of my reasoning behind it. Well, so let's look at what it is. Your real final is only going to have 10 multiple choice. This one here has got a lot more questions, so you can get an idea of questions that I ask and how I ask them. I think it's got 40 questions, yes. Now, in multiple choice, all I will see from you is on a piece of paper that question 39 is B. I don't want to see working. There probably will be working for some of them, but that's fine. Don't show me it. It's multiple choice is it's right or it's wrong, and there's one right answer, so pick it. Let's pick a random example of that guy. Here's question 26. In the Salk vaccine field trial of 1954, it's a classic in the statistical medical world. Does anybody know what that vaccine was for?
Oh, I thought you said salt vaccine, and I was like, why are
No,
you injecting salt?
Was it polio?
SALK. It was a polio vaccine. Polio was it was a vile disease, right? It affected the limbs of lots of kids, and they ended up in wheelchairs and all, and they didn't typically live so long as well. So that was a big thing, polio, way back in the day. So anyway, the Salk vaccine field trial of 1954, participating children received a vaccine or a placebo in a randomized, placebo-controlled, double-blind experimental design, right? I put every word in the sentence book there, right? The response variable was whether or not the child was diagnosed with polio during the following summer. The main purpose then of using a double-blind experiment was, which one of those four is the best fit?
C.
Yes, basically C. Now, you might say the others are correct, or two of the others are correct, but when you do this, you always pick the best answer, not the one that's correct, because there might be two things that are correct, but the main reason would be that. Unconnected with this question, but the Salk vaccine wasn't conducted that way the first time. What they were worried about when they did they did a small version, just to get rid of the kinks, and they found out when they did the small trial that people who were vaccinated, the children who were vaccinated were, rewind, they found out that one of the major places that you got polio was in swimming pools, right? It was in the water. And swimming pools was associated with people who are richer, because you had a swimming pool, right? And poorer people didn't go swimming as much. And they found out that when people were told or knew that their child was vaccinated, those children would continue to do behavior that made them more likely to catch polio. And it was actually influenza there, because it wasn't a perfect vaccine. You still caught it, but fewer people caught it. And it was really screwing up with the data bad, so they did a double blind. That's the bottom line. Really interesting, because that kind of is the poster child for almost everything that came after it. Right. So they used the double blind because of this, and they found, that it's very important to tell nobody nothing. They found out when anybody, including the doctor, knew about it, he could influence them even indirectly. So, multiple choice.
Professor Robertson,
Yes.
I have a quick question.
Yes.
Will we have lectures every day next week minus Thursday, or is this the last
No.
week of lectures?
Yeah, that's a good question. It's going to be. complicated, mumbly answer, but here goes.
Okay.
For the rest of this week, we are basically finished. So for the rest of this week, what we're going to be doing is I'm going to be just going over topics. So it's revising for the final. So we've actually covered really quicker than I thought we were going to do, but that's not a bad thing. Next Monday, there's the test 5. Test 5 doesn't need to be done by quite a few of you. Because I only count the best 4, you might just decide not to do test 5 and use that day to revise for your final. And I totally understand that if you choose to do that. If you've missed a test or you want to improve one of your grades, you should turn up for test 5. But the rest of next week is exam week, so I won't see you until Thursday.
So isn't that the same name?
I didn't catch that, Ashley, and your voice broke up a
Is
little.
the final at about the same time?
It's
Longer though?
It's 3 hours, and it's, don't quote me on this because I only saw it once and I didn't pay too much attention. I think it's 10 till 1 on Thursday, but it's in the syllabus. You can double check that.
Okay.
But it's a 3-hour thing. It also involves at the end uploading your working into Canvas. And so you just stay online until everything's done. That way I really want to make sure that everything is uploaded into Canvas. There won't be such a big time limit. You know how like you've got half an hour to upload it to Canvas. It'll be almost like an open-ended Canvas. You know, if your camera loses its battery power or whatever, we'll figure a way around it. Because it is such a big thing. On the final, everything will be closed out. The only thing you'll see in WebAssign is that dummy question that allows you to use SALT. That's the only thing you'll see in WebAssign. And the only thing that you'll see, excuse me, in Canvas will be your PDF of your final exam and the T distribution table, because you need that for some questions.
This document, it was practice, final, and solutions. Where are the solutions located?
Right at the end. So let's scroll down. So here is section
Sorry, I thought
2.
part 9 was, or I thought page 9 was the end. It just,
Oh,
never mind.
God, no.
Okay.
This thing goes, this is a manual, right? This book, you could call this a book, right? So here is section 2. And when you do section 2 questions, I really do need to see your working. Because if you screw up, I can't give you anything. If I see the working, I can give you partial credit. And it contains lots of questions. I've randomly stopped here. And I've stopped too far. There's your last question. So you recognize 18 and 19 are essentially what we've been doing right now, this last week. Here are the solutions to the multiple choice. And here are the solutions that you're asking about, David. So
I think a while ago, did you say that the other tests we had like a solutions page uploaded or something?
yes, I do have them, with the exception
I don't
of
see
test
any
4.
of those.
Oh, okay. Well, this is a solution to that one. Let me get out of this guy. Go home.
So I only have like the
Yeah.
top piece. It's the practice, T distribution, and
Oh,
a couple of general things like schedule.
There we go. For some reason, I forgot to publish it. It'll be visible now. It's under a thing called past topics. And there's the solutions to the tests. So if you upload Canvas and look for a tab called past topics, you will find the solutions to the tests.